Let's work on question 18. All right, question 18. A rectangle is inscribed with its base on the x-axis and its upper corner on the parabola y equal to 10 minus x squared. What are the dimensions of such a rectangle with the greatest possible area? I wonder if you have any difficulty with this question. This is a max and min question. It says find the greatest possible area. That's a comparative term. So basically, we were supposed to find the calculation of the area and figure out a way to make the area as big as possible. So we're maximizing the area, try to find the maximum value of the area. So you got to find the function for the area. Then we find the maximum value of the function, which will then solve the maximum area. So if you have any difficulty, feel free to let me know. I can switch to one of those questions that we have on our homework. This used to be on my homework set. This semester, I think I changed it slightly. But you can comment on whether this is a good example for the optimization question. But if nobody comment on it, this probably will be something I will try. And we can also use one of those business question as our final exam question on the optimization question. But anyway, optimization is section 4.3. You can find all your homework questions related to optimization on 4.3. And the idea on optimization is whatever you're trying to maximizing or minimize, you have to find the function to model that. Once you find the function, the rest is calculus, which is looking at the derivative, study increasing, decreasing, and then by increasing, decreasing, you find out when it reaches a maximum or minimum. All right, so this function. If we want to find the greatest possible area, first you have to draw this rectangle that is being described in the question. What are the dimensions of such rectangle with greatest area? So what rectangle? It's a rectangle that's inscribed with the base on the x-axis and the upper corner on the parabola on the graph of y equal to 10 minus x squared. So I draw the parabola y equal to 10 minus x squared right here in the picture. And this is the rectangle. So the rectangle will have two corners on the x-axis and two of the upper corner on the parabola. It's symmetrical. The symmetrical. The parabola is negative x squared. It's an even function for the parabola, so that's why it's symmetrical left and right. The left side and right side of the entire picture is identical, left and right, symmetrical, mirror image of itself. So we want to be able to quantify it. If we have y equal to 10 minus x squared, then the x value and the y value is quantified. So you can identify the upper corner xy is a coordinate. So the distance horizontally is x, the distance vertically is the y. So the y is the height or the width of the rectangle. Twice of the x value is a length. So the length of the rectangle is 2x. The width of the rectangle is y. Now, if we represent the area with 2xy, we will be looking at a function that has two variables, which is something we might do in calculus 2. But now we have y equal to 10 minus x squared. That allows us to replace the y, the letter y, by 10 minus x squared. So this function 2x times 10 minus x squared, parentheses, that formula described the calculation of the area, the blue area, the blue rectangle in the picture. So now we have this function. We will try to use calculus method to find the highest value of this function. And then the way we do it is to find, first we simplify the function, 2x times 10, 20x, 2x times x squared, 2x cubed. So we simplify the function, and then we can find the derivative. After finding the derivative, we want to find the critical point, because the critical point allows us to study increasing, decreasing. Find the increasing, decreasing, we can find the max and min. So we will set the derivative equal to 0, 20 minus 6x equal to 0, which then means that 6x squared equal to 20, x squared equal to 10 over 3. So x equal to square root of 10 over 3, which is roughly 1.82574. That's the critical point. Here we're finding the upper corner, which has a positive x. That's why I didn't x squared equal to 10 over 3 has two solutions, positive and negative. You see there are two corners, but we're trying to find the upper right corner, the positive x. So I use the positive x value. And then now all we have to do is find out, do we have a max and mean right there? I did something to confirm when x equal to 1.82574, we do have a maximum. How do we know it's a maximum? We find the, does it make a maximum? We find the second derivative. So we already have the first derivative. Derivative of the first derivative is the second derivative. So the second derivative is negative 12x. Now you use the x value equal to 1.82 to replace x. So negative 12 times 1.82574. We got negative 21.9, which is negative. That means the function is concave down. If the function concave down, right in the middle where the derivative equal to 0, you see that has to be a maximum. This is called a second derivative test. When the first derivative equal to 0 and the second derivative negative, we have a maximum. That's what's being shown in the picture. At the lower left corner, I draw a little curve to indicate for the function f, we have a maximum there. So we know that if x equal to 1.82574, we have a maximum area. Now the question asks for dimension. So what was the dimension? Right, like those are the calculate dimension. Dimension is the length and width of the rectangle. The length is essentially equal to 2x, so x times 2, which is equal to 3.652. The width of the rectangle is the y value, which equal to 10 minus x squared. Calculate the 10 minus x squared when x equal to 1.82574. Then the width equal to 6.6657. So right in that block, I blocked out the final answer to the question, which was the dimension for the rectangle. I hope that explanation works okay. But if this felt like overly complicated, we can revert back to those bits in this question that we learned in 4.3 using them as the final exam question. Feel free to comment on this if you have any question, and we can switch it to a different version of it. And that will be it for this question.